Okay, Aubrey, this is the start of 3-1. We are starting chapter 3. Chapter 3, folks, we got to step up our A game on chapter 3 because chapter 3 is the chapter that begins logic and reasoning, and it is the introduction into proofs, which geometry is like notorious for being icky for, right? Geometry is icky because of proofs. You have to prove something is true and not true, right? Okay. What?
Why would I have to prove it's a triangle if I can clearly see it's a triangle?
No, we're not proving that things are triangles. No. No. No, that's not one. That's not a thing. Okay, so proofs, that's where we're going to start in this chapter, and then it will carry on in the next couple chapters, all right? So chapter 3, here's the homework assignment for chapter 3. Let's rock and roll. We are starting with conjectures and counterexamples. Okay, write this at the top. Those are big words, so that's why I'm going to dumb it down for you. A conjecture. Here's what a conjecture is. A conjecture is a conclusion or a generalization about things. Okay? Conjecture. It is like telling me what the pattern is, basically, right? Is identifying a conjecture or a conclusion. A counterexample is an example that counters what it is we're saying, right? A counterexample, okay? It is something that proves a statement false. An example that proves a statement false. So, for example, are you ready for this? Let's say here's an example. Let's say I have x is less than x squared. Is that always true that x is less than whatever it is? Like I'm thinking like 2. Let's say x is 2, right? 2 is less than 2 squared, true? Yep. Is it always true? Give me a counter example.
Half. 1/2.
1/2, Colton said. 1/2, if I take 1/2 and I square it, it becomes? 1/4. Is 1/2 less than 1/4?
No.
Nope. So 1/2 is a counter example. Does that make sense? What's another counter example? How about 1? Is 1 less than 1 squared? 1 is equal to 1 squared, right? So these are all counter example. It's proving my statement false. Got it? Okay, so conjectures is developing a pattern or giving me a conclusion about a pattern. Counterexample, prove something false. Here we go.
So would a conjecture be like x plus 4?
Depending on the pattern, yeah.
So like,
We'll get to that. Okay, so patterns and conjectures. Write a conjecture that describes the pattern in the sequence. We have appointment times that are 8:30, 9:15, 10, and 10:45. What's my conjecture?
45.
Each appointment is 45 minutes after the previous appointment. The next appointment time will be at
11:30.
11:30 a.m. Yeah? So it says write a conjecture. So this part is my conjecture. 45 minutes in between all appointment times, and then the next appointment is 11:30. Those are the two things that you have to have. Then write your next term in the sequence. So conjecture, next term. Conjecture, next term. All right. Example 2, make a conjecture and then draw some examples to support this. So it says, make a conjecture about the sum of the squares of 2 consecutive natural numbers. Okay, the sum of the squares of 2 consecutive natural numbers. Consecutive natural numbers means consecutive counting numbers, like 1 and 2, or 2 and 3, or 3 and 4, or 4 and 5, or 5 and 6, or 6 and 7, or 7 and 8, or 8 and 9, and 9 and 10, and blah, 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 all the things, right? 1 and 2 are consecutive, but if we square them,
5.
okay, this gives me 5. What does this give me? 4 plus 9 is 13. Okay, 6 squared is 36. 7 squared is 49. That is 85. 10 squared is 100, 11 squared is 121, so that is 221. Okay. Give me a conjecture. What is a conjecture? What can we conclude about all of these? If I add, they're all odd numbers.
That's what it means?
Yeah, we're developing a pattern, right? Anything else I can say? Are all of those numbers divisible by 5? Not necessarily, but they all have to be odd numbers, right? Okay? Every time you square two numbers that are consecutive and add them together, it will give you an odd number, no matter what, right? Okay? What happens if I just add the consecutive numbers and not square them? What will it be? Like if I add 1 and 2, and 2 and 3, and 3 and 4, what will that always be? That will always be odd as well, right? Okay, we're developing patterns. Got it? Coming up with a conjecture, okay? All right, so the sum is always odd. That's my conjecture. Got it? All the result will always be odd, okay? Next, example 3. These are geometric conjectures. So maybe we're like drawing a picture that follows the pattern, right? Make a conjecture about the relationship between the segments joining opposite vertices of isosceles triangles. Okay, back up. What is an isosceles, not a triangle, isosceles trapezoid? What's an isosceles trapezoid? Yeah, trapezoid means two sides are parallel. So these top and bottom are parallel. And isosceles means those two sides. Can we draw a trapezoid where the two sides are not the same?
Yeah.
I'm thinking like, let's say I have this thing going on, right? Is that a trapezoid?
Yeah.
The top and the bottom are parallel, right?
Yeah, it is.
But this side is obviously not the same as that. That's a trapezoid, right?
Yeah.
But not an isosceles trapezoid. This is isosceles trapezoid. Okay.
Perfect.
We're talking specifically about isosceles trapezoids, but joining the opposite vertices. So like this guy. What's he called? A line? Starts with a D. It's called a diagonal. This is a diagonal. So we're making a conjecture about the diagonals, right? That diagonal in comparison to this one. This diagonal in comparison to this one. This diagonal compared to this one. What's the conjecture? They all make an X, but let's more than that, right?
Triangle.
They make 4 triangles. What else?
Intersect.
They intersect.
The trapezoid are 4.
What's the same?
They're
Is this the same length as this one? Is that true in all trapezoids? Is this diagonal the same length as this one? But in all isosceles trapezoids, the diagonals will be the same, right? Not in a regular trapezoid, because one will be shorter than the other, right?
Well, not necessarily.
But yes, it will be.
But a regular trapezoid could also be an isosceles.
But then it would be an isosceles trapezoid.
But then it would still
No.
be regular.
No.
Isn't it the whole like a rectangle is not a square, but a square is always a rectangle?
Yeah, but you want to go with the most specific name.
I'm about to flip this table.
Okay, whatever. Sure.
Go ahead.
All right, so there you go. So the diagonals will always be the same length. What's another word for the same length? The segments joining opposite vertices of isosceles trapezoid. I'm going to go the segments joining opposite vertices, the diagonals. That's too many words, and let's shorten it a little bit. The diagonals of an isosceles trapezoid are congruent, meaning the same length. Yeah? That's a conjecture. No matter what, those diagonals will be the same length if it's an isosceles trapezoid, right? Not in a regular trapezoid, but an isosceles trapezoid it is, right? We can make that conjecture or make that like conclusion or diagnosis or whatever, right? Okay, here we go. Example 4. The table shows the average price of gasoline in 2010 through 2018. Ooh, oy vey. Make a conjecture about the price of gas in 2019. What do you think's going to happen? It's probably going to go up again, right? It is on the rise. Like it's fluctuating. Here it went up. From here to here it went up. From here to here it went up. Then it went back down, 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 down. Now it's on the rise again. Up, up. It's probably going to go up again, right? So if I were to guess, I mean, at some point it's got to go back down again. But I don't think it's done rising yet, right? Like it's not finished the pattern of rising. So I'm going to say, it says a conjecture. In 2019, the price of gas will continue to increase, right? Something of that nature. That's the pattern. I'm just using my context clues to figure out logic, like reasonably. Like, let's just be reasonable about this, right? We're making conclusions. I'm going to guess that it's probably going to increase, right? We're on video. Wyatt, shut up. Okay, counter examples. Last thing. This is the last concept, is counter examples. I already said counter example is something that proves it false, right? It proves something false. Now, false. A counterexample could be three different things. Ready for this? A counterexample could be a number, like the example that I gave you before, where I said x is always less than x squared. You're like, no, that's not true when x is 1/2, right? That is a counterexample that is in number form. But I could also have a counterexample be a drawing, right? If I draw you a picture that proves it false, I could do that. Or it could be a statement, right? That proves something false. Okay, it doesn't have to be a number, but it could be any of the other two forms, right? So any of those three forms can prove something false. Okay, find the counterexample. So find a counterexample to show that each conjecture is false. If n is a real number, what's a real number?
Not a big one.
Any number that you can think of. What is not a real number? Pi is a real number. Pi is an irrational real number. I. The only thing that's not a real number is an imaginary number, which is I, right? Have we talked about I before in Algebra 2? I is the square root of a -1, right? Or I squared is -1. Okay, those things. So, real numbers. So, any number that you can think of that doesn't involve an I. Then negative n is a negative number. True or false? If n is a real number and I put a negative sign in front of it, that makes it a negative number.
No, negative numbers.
If it's a negative number to begin with, is a negative number a real number? They use -4 as a counterexample. If negative number is the real number that I'm choosing and I put a negative in front of it, does that make it negative? No, that makes it positive. Two negatives make it positive. So their counterexample was, what if n is -4? You only have to do one counterexample to prove the whole thing false. I said, I found one flaw in your statement, therefore the whole thing is wrong, right? That whole statement is wrong. Because I could have provided a ton of counterexamples, right? But you only have to pick one, right? Okay? All right. Here is a drawing or a geometric thing that's going to be a counterexample. So it says, angle ABC is congruent. This is the symbol for congruent. Congruent to angle DBE. Those two angles are congruent, meaning the same size. So if one is 40 degrees, the other one's 40 degrees, right? Then angle ABC and angle DBE are vertical angles. Okay, hold up. Vertical angles. Are vertical angles congruent?
Yeah.
Vertical angles are the ones that go like this. Boop. This angle and this one.
Yes.
Are vertical angles always congruent? Yes. But are two angles that are congruent, are they always vertical? Are they always across from each other? No, here's my counterexample. Let's say I have this going on. Here is this angle right here, and I've got that thing. And I've got this angle going on, and I've got that thing. Are those two vertical angles?
Yeah.
Are they across from each other?
Yeah.
Using two straight lines. Vertical angles have to have two straight lines across from each other, right? This angle is not vertical to this one, but they are congruent. So this thing right here is my counterexample. That is a drawing of a counterexample. Do you see that? Yeah? Yeah? Okay, let's do another one. Let's say, here's my example. If two angles are supplementary, then they are a linear pair.
No.
What does a linear pair mean? They form a line, right? Like this angle and this angle are a linear pair, but they are supplementary. So why is that not true?
Because if you're aware that two angles equal like 90 degrees, for example, but they're not a linear pair.
If it's a linear pair,
Like
then they have to be supplementary. But if they're supplementary, they're necessarily a linear pair. That's kind of like if it's a rectangle, if it's a square, it's a rectangle. But if it's a rectangle, it's not necessarily a square, right? We'll get to that.
Yeah.
Okay, in chapter 6. All right, so here's my counterexample. I have this angle right here. How much do you want that angle to be? What does it look like? How big does that angle look like it is?
20 degrees.
No, that looks bigger than 20 degrees. I'm going to say 45 degrees. Okay, let's put another angle over here that looks like how much? How much would that have to be?
75. No.
You're an idiot.
135.
Yeah, 135.
He has to be 135, right? Are those two angles supplementary?
Yes.
Yeah, 45 plus 135 adds up to be 180, but are they a linear pair? So this right here is my counterexample. I just have to draw two angles that are supplementary that are not a linear pair, right? That is my counterexample for that statement. Got it? Okay, let's do this one right here. Check. Find a counterexample to show that each conjecture is false. If n is a real number, then 1 over n is less than n. if n is a real number, then 1 over n is less than n. Here's what you're thinking. Let's say n is 2, right? Then 1 over 2 is less than 2. That's true.
Yep.
1.
Is it always true?
Equal.
Okay, let's say n is 1. If n is 1, then 1 over 1 is less than 1. Is that true?
No.
No. So counterexample, n is 1, right? Yeah?
You can do like point.
Okay, there's a lot of these. Select all that apply. If n is negative 3, and I do 1 over negative 3 is less than negative 3. Is that true? Is negative 1/3 less than negative 3?
No.
No, we're doing negative numbers. So this one is a counterexample. True? Okay, 1/4.
Nar.
Okay, 1 over 1/4 is less than 1/4.
That equals 4, so no.
Right? This is 4 is less than 1/4. So that's a counterexample. 5. 1 over 5 is less than 5.
That would
That works, so that's not a counterexample. Does that make sense? Okay. What does this say? 100? 1 over 100 is less than 100. That's true, so that's not a counterexample, right? Okay. So it will be a counterexample if it's not a number that is larger than 1, right?
It could be 1 point.
Right? It could be 1/2 or it could be 1/4, right? But as long as it's not larger than 1, right, it will not be a counterexample. So any number 1 and below will give me a counterexample. Okay, whatever. If a line intersects a segment at its midpoint, then the line is perpendicular to the segment. Okay, here's my segment, and I have a line that's cutting that in half. Do those things have to be perpendicular? Like I have something that's cutting it in half. That is perpendicular. But does it have to be cutting it? Does it have to be perpendicular if it's cutting it in half?
No.
How about like this? Is that cutting this segment in half? Yeah, but it's not perpendicular, right? It's not 90 degrees. This is my counterexample. That's a drawing. That's a counterexample. Make sense? That was part B. Good? Do we see how this works?
No.
Okay.
Can we do number 2?
What you talking about?
Number 4.
Number 2. Write a conjecture to describe the pattern in the next sequence. What's the conjecture for number 2?
Every time you add a 2 to the end.
You're adding another digit of 2.
10 times the previous number plus 2.
Oh,
Yeah.
Can I just do
that's a good one. I like that. Did you hear Jacob? Instead of saying you're adding a 2 to the digit, they're saying this number times 2 but plus 2, right?
Times 10.
Or times 10, not 10, not 2. Times 10. If I take that times 10 plus 2, that gives me 22. If I take this times 10 plus 2, it'll be 222. If I take this number times 10 plus 2, that gives me that number, right? Okay, so what's the next number? So what, okay, so hold on. My conjecture is the next term equals times 10 plus 2, right? That's my conjecture. The next term in the sequence is, how many 2s? 5 2s? 1, 2, 3, 4, 5. That's how you do this one. That's number 2. That's a lot of 2s. Woo!
222.
Yeah. 22, 222. Yes.
So number 4 we just
Okay.
do like,
Good? All right, there you go. Goodbye.